Hi friends, good evening, and let me just check if everything is working as expected. Just give me a minute. I'll just check if everything is working as expected before we dive into the session itself, right? So just give me a minute. Uh, cool. Okay, so can you please confirm in the chat window if everything is working well? I have a chat window on a different computer so that we have more screen space for the questions today. I have an alternative. I'm actually checking it on my phone. So could you please confirm if everything is working as expected in the chat window? If anybody has problems, I'll look into it from a technical side. So can you please confirm if everything is all right from the chat window perspective? Okay, you're audible, you can see. Cool. So just a quick update about DLD. We have been updating roughly about 2 hours of content. We should be done with it hopefully by the end of this month. And there is also a question about DLD versus CO. So DLD content is already there. It's not that the content is not there. I'm redoing it because students requested for it. All of DLD content is there. And even when we created CO content, don't worry about it. You will be able to solve CO problems even though you have not done DLD. If you want to see only videos done by me in DLD, you will have to wait for 1 more week. We're already uploading at least almost 3 hours of videos regularly. You should have all of that content. Again, you can go check it. There are a lot of free videos which I have redone. We're also putting in non-free videos also. Okay, so don't worry about it. Again, when I created the CO content also, most of the content in most of the subjects that we have designed is such that you can pick any subject and go with it with almost no prerequisites. Maybe you just need to know a little bit of C programming, right? So that's how we created most of the subjects. So don't worry about it. Please be patient because I'm uploading content at full speed. I don't want to mess up with the quality. I always look for the best quality that I can give, and we should have whole of DLD done by me personally by the end of the month, right? And constantly I'm uploading this. We are processing the videos and uploading the content, but there is already content from another professor. Okay, so don't worry about it. Any problems you have, do reach out to us. Cool. Sounds good. So let's dive into, it's already 7 p.m. So let's get into operating systems itself. Very interesting topic. So let's dive into it, right? So let me just check if everything is working as expected. Give me a second. Okay, I think, okay, the comments, I'm able to see the comments. I just wanted to make sure because I'm seeing the comments on a different computer. Okay, so cool. Yes, cool. Okay, thankfully our team is also joining in. So they will also be able to answer some of the questions which I cannot. And I wanted to give more screen space to the questions instead of the chat, but I'm looking at it on a different window. Cool, sounds good. So let's get started. This is the first live session of operating systems and let's dive into it. So here comes the first question. The questions are slightly big. That's why I wanted to use the whole screen. This is a medium level, medium hardness question by Gate standards. Just please read the question carefully. If you read the question carefully, it is simple and straightforward. Again, let's get to solving the questions. Again, anything that we cannot answer as part of these live sessions, feel free to email us. We are there to help you. If you're a registered student, we'll answer with higher priority. Even if you're not a registered student, shoot an email. We'll try our best. Okay, as soon as people start putting in the answers, I will dive into the solution. Or in other words, as and when sufficient number of students have answered this, I'll go into the solution. Okay. Okay, some of the general questions, I'll answer them between questions or at the very end. Okay. Again, please be careful. Please read the question very, very, very carefully because it's so easy to make mistakes in these simple questions. Again, look at it. It says longest job first scheduling algorithm. Okay, I see a couple of you putting in your answers like 2 and 8. Please redo your answers. For every question, we mention what is the hardness. This is medium level question by Gantt standards. We mention whether easy, medium or hard. Since this is the first iteration of all the subjects, we are only doing easy and medium problems. As we come closer to the exam, we'll start doing more and more medium and hard problems. Cool, I see a bunch of answers here. Those of you who want a small hint, remember that longest job first is non-preemptive, right? So this is non-preemptive, right? That's one thing that many people mess up with. Remember that it's a non-preemptive scheduling algorithm. That's something that you have to be very, very careful with. Again, since this is an interactive problem solving session, I recommend everyone to attempt these questions. Okay, I see answers all around the place in the chat window. I see answers like 2, 5, 7, 8. I mean, all sorts of numbers. Of course, all of them can't be correct, so you have to think carefully. Again, please read this note if that helps you. Cool, since some of you, or at least a good chunk of you, have answered this question, let's get into the solution, right? So let's draw this timeline of sorts, right? So imagine we are at timestamp 0. At timestamp 0, none of the processes are available. So up to timestamp 2, there is no process, right? We don't have any process to schedule. At time 2, we get process 0, right? That's the only process that's available. So we schedule process 0 now. And remember that longest job first is a non-preemptive scheduling algorithm. And its burst time is 8, which means up to 10 units of time, because the total is 8 units now, up to 10 units of time, P0 will be executed. Now, the moment you reach 10 units of time, you have all these three, P1, P2 and P3, all of them are available. Look at this, all of them are available now. That's important, right? Now, what does the question say? The question says, what is the maximum value of X to ensure that the completion time of P2 is minimum, not P1? Look at the question here, the maximum value of X. X is the burst time corresponding to P1, but the question here is, what is the maximum value of X to ensure that the completion time of P2 is minimum? Right? This is very important. Now, at timestamp 10, you have P1, P2 and P3, all of them. Right? Now, remember, notice that this has a more burst time, which means if you use the longest job first algorithm, obviously P3 will get scheduled. Again, remember, you want to complete P2 as fast as possible because you want the completion time of P2 to be minimum. So what is the order that you want? You want, obviously P3 will be executed first because its burst time is more. Then you want P2 followed by P1. This is the order that you want to create the completion time of P2 to be minimum, given that we can choose the X. So P3 will be scheduled now. So if you schedule P3, P3 has a burst time of 7, which means at 17 units of time, P3 will be complete. So P3 is also complete now. Now we are left with P1 and P2, right? Now if you have P1 and P2, you want X to be less than 6. Why do you want X to be less than 6? Because if X is greater than 6, then P1 will get scheduled, which is delaying P2. We want to schedule P2 now. To schedule P2, your X has to be less than 6. But can X be also equal to 6? That's another thing. Other thing that you should always think of. Can X be equals to 6? Imagine if X equals to 6. Then what happens? Then both process 1 and process 2 have the same burst time. In that case, we have a tie. In the case of a tie, the minimum arrival time would imply higher priority. Notice that P1 has a earlier arrival time. If both of them are 6, then P1 will get scheduled and not P2. That's the reason why this note has been given. That's very, very important, right? So it cannot be equal to 6. So x is less than 6 and x cannot be equal to 6. So what is the units of time that is the maximum value of x? It is equal to 5. That's it. That's the answer, right? Again, if you read the question carefully, this is actually an easy question. The reason we marked it as medium hardness is because of this tricky statement. Because we want the minimum value of x to ensure that the completion time of P2 is minimum, right? That's the tricky part. That's where a lot of people get confused. Otherwise, this is very simple problem, right? Cool. Let's go to the next question now. Okay. So this is a simple problem. Please read the question carefully. Again, some of the questions that I could not answer are also being answered by our team. And if something cannot be answered in a simple chat, please shoot an email. We'll try to respond back as soon as possible. Somebody says the previous problem is hard. Come on, which means you have not come prepared. It's a very typical medium level gate problem. Again, the easy, medium, hard all depends, the tags that we are giving are only based on the gate examination standard, not your hardness or my hardness or some X person's hardness. I'll give a hint after a few, maybe after a few seconds. Somebody is asking what types of questions are asked in product-based companies. Please solve the problem. We are here to solve gate problems here. Please focus on that. That's the objective here. I will give a hint only after giving ample time for people to think. I will not give a hint at the very beginning. I will give ample time for people to attempt. I'll give a hint for those who are a little stuck. Okay, I see a lot of answers being put in. Some of them correct, some of them not so correct. But good. People are getting it. I don't think I need to give a hint in this problem. Cool. Okay. For those of you who are stuck in getting started, if you've already started solving it, cool. If you're stuck, try to use probability here. Try to use some simple concepts in probability. That's the only hint I'm going to give today for this problem. Okay, a lot of you got it right, which is good to know. Which is good. A lot of you are getting it right. Okay, so let's get into the solution itself. All this is considered a multi-programming system with degree 6, which means a maximum of 6 processes can be processed parallel or simultaneously by a single processor. Okay, assume that each processor spends 40% of the time waiting for I/O, right? So what is the probability of one process waiting on I/O? The probability is 0.4 of one process waiting for I/O. Now the question here is, each process is independent of one another. Then the CPU utilization is. Look at this. Here all you have to say here is, what is the probability that all 6 processes right? What is the probability that all 6 processes are waiting for IO, right? When all 6 processes are waiting for IO, the CPU is not being utilized at all, right? What is the probability of that happening? Look at this. The probability of one process waiting is 40%. Since all the processes are independent, the probability all the processes are waiting is 0.4 power 6, which is roughly equal to, if you use a calculator, you will get this number, right? So this is nothing but 2 power 12, right? If you think about it, this is nothing but 2 power 12, right? 2 power 12 is 4096. You don't require a calculator if you're a CS guy. This is straightforward to compute, right? So you get this number. Now, what is the CPU utilization is basically 1 minus this value, because for this much, with this probability, the CPU is completely idle. It's not doing anything when all the processes are waiting, which means the CPU utilization will be 1 minus this whole value. Now, if you do 1 minus this whole value, you get 0.995904, and it says round off to 3 decimal places. So this is equal to 0.996. So your CPU utilization is 99.6%, or in other words, 0.996. Right? Very simple problem. Again, I'm happy that most of you got it and mapped it to the probability problem. It's a very simple, easy problem by Gantt standards. Okay, cool. Let's go to the third question now. Okay. I've squeezed this in. Cool. Please read the question carefully. Again, this is a medium question because it's very easy to get confused in this question. Please read the question very, very carefully. I cannot emphasize that. Especially read this statement very, very carefully. That's where a lot of people will make mistakes. Take more time, that's okay, but I want you to get it right. Read this statement that I just mentioned very, very carefully. I'm having water. I avoid eating after 7 p.m. So I was actually sipping water. I think my microphone is pretty decent. It's picking up even the smallest of noises. Good. Again, this is a standard round robin problem. You just have to be careful in reading this statement carefully. That's where, again, there is this small point about tie breaks, but many people I've seen, even when some of our teammates were solving the question, they messed up reading this part. So be careful there. Again, folks, it's very important for you to revise and learn these concepts and come for the session. Otherwise, you will not be able to solve. Again, this is not an easy problem, but it's a very standard problem by Gantt standards. Okay. Again, take your time. Go slow, take your time. Don't worry about it. Remember, it is asking for the second last time when P3 enters into the ready queue. It's not asking the last time, it's asking the second last time. That's important. You have to be careful with that. Take your time, it's okay. I mean, you might have to draw more stuff for this question, so it's okay. Take your time. Let's go through this. Again, I recommend everyone who is coming in for these sessions to quickly revise at least some of the basic concepts so that you can actively participate. It's very common to forget concepts. You could just download our freely available notes and revise from it. If you've already learned operating systems, you can revise through that notes very, very quickly. Again, somebody thinks that these questions are hard. Please don't think so. You are just being defeatist. These are very standard questions at gate level, and we have solved tons of similar questions in our course videos, in PYQs, in previous year problems, etc. Right? So if you're not prepared, obviously you'll not be able to solve. Right? It requires practice and patience. Okay, cool. A good chunk of you have answered the question. So let's get into the solution. I've already drawn these diagrams because it's harder to draw all of the charts, everything in this small space. So I've already pre-drawn it. Thankfully, our team has helped me with that. So let me go into it, right? So look at this. So we have this P0, P1, P2, P3 arrival times and burst times, right? So let's go step by step. Okay, so cool. So at the very outset, what are our burst times? Are 3512, right? 3512. Okay, cool. So let's write down, right? So this is our process. These are our processes, P1 to P3. These are our arrival times. These are our original burst times. As we keep allocating these processes some CPU time, we keep striking it off and keep reducing it. Remember that the time quantity that we have, or the time quantum we have, is 1.5 units, right? So let's go here. Let's start drawing the Gantt chart. Also, let's keep the ready queue handy, right? So let's see. Let's go step by step. I'll keep jumping. I'll keep scrolling through and start explaining step by step. Okay, so let's go. So at the very outset, 0 timestamp, none of the processes are available, which means from 0 to 1, there is nothing to do. At timestamp 1, we got process 0. Only process 0 is there in our whole system, nothing else, which means your process 0 would have entered the ready queue at timestamp 1, right? First it would enter the ready queue. Since the CPU is free, it will get dequeued and it will be assigned the CPU. So P0 got assigned at timestamp 1. Since it can stay with the CPU for a time quantum of 1.5, it spends 1.5 units of time. So we are right now at this timestamp. Okay, so let's keep a track of that. So we are right now at 2.5 units of time. And what happens now? This gets deleted. We've already spent 1.5 units of time. So we are only left with 1.5 units of time. And what is our current time? Our current time is 2.5 units, right? With at 2.5 units, notice that P1 would have also entered into the ready queue. Look at this, P1 would have also, so let me write the current time now. The current time is 2.5, right? So P1 would have also entered the ready queue at timestamp 2, because P1 is being generated, its arrival time is 2, which means at timestamp 2, it would have gone into the ready queue. It is waiting. At 2.5, your P0 would get preempted and P1 will get a chance, right? So what happens now? At 2.5, P1 will get a chance. Again, when this happens, P0 is not yet complete. P0 still has to spend 1.5 units of time with the CPU. So it will get added to your ready queue. So P0 joins the ready queue at 2.5 units. That's important to keep note of, right? Okay, so now where are we? So we are here. P1 spends 1.5 units of time. Now we are at 4 units of time. At 4 units of time, P2 is not there, P3 is not there, right? So its actual burst time is 5. It has spent 1.5 units of time, which means it is still left with 3.5 units of compute, or 3.5 units of time. P0 also has 1.5 units. Now in the queue, P0 is ahead of P1. So P0 now gets scheduled, right? Look at this. P0 now gets scheduled. At this time, P1 will again join the queue, right? So in your ready queue, the only trick that you have to do here is, in your ready queue, just make sure you write down the timestamps at which each of these entities or each of these processes is getting added, right? Cool. So now we are at timestamp 4. P0 gets a chance. Again, till timestamp 7, look at this, till timestamp 7, P2 is not yet arrived, neither P3 has arrived. So till timestamp 7, P1 and P0 will keep taking turns one after the other after a certain number of times. That's the key idea here, right? Now at 7 units of time, look at this. Now if the time is 7 units, now what happens? Look at this. This is where we have to be very, very careful with. At 7 units of time, we would have spent, look at this, at 7 units of time, we've already spent all the, P0 is complete now because it got 1.5 units of time. P0 is complete. Now let's look at P1. P1 completed, look at the total time. P1 total burst time is 5. It spent 1.5 units here, 1.5 units here. So it's still left with 2 units. So P1 is still left with 2 units. P2 just arrived, right? So now let's look at the scenario. You have to be careful with drawing this. That's all, right? P2 arrived, P1 is also there, right? Now both of them at 7 units of time exactly. Look at this. Exactly at 7 units of time, there is a very interesting phenomenon that's happening. P2 arrives and P1 also got preempted right now. Look at this. P1 also got preempted now. Now both P1 and P2 are in the queue. Now what do you give preference to? Look at this. In the queue at 7 units of time, both P1 and P2 are there. What do you give a preference to? Look at the note that is mentioned here. In case of a tie break, process with lower ID will get higher priority, right? So now what happens? P1 will get a priority. So here if you notice, at this point of time, both P1 and P2 are competing for the resource or for the CPU. Both of them are there here, which means now because P1 has the lower process ID number, P1 got a shot. That's important. Now P2 still stays here. P1 spends some time, right? P1 spends 1.5 units of time. Then P2 gets a turn again. Now look at when does P3 come into existence. Look at it. When does P3 arrive first time? P3 arrives the first time at 9 units of time. Our question is all about P3. So at 9 units of time, let's see, again, if you continue drawing the same chart, at 9 units of time, P3 is generated into the, P3 is added to the ready queue. But at 9 units of time is somewhere here. At 9 units of time, P2 is currently executing and P1 is already there in the queue. So now P1 gets scheduled, P2 is complete, right? P3 is executing. Look at this. So by the time P1 completes this, how many times P1 completed? P1 completed, P1 completed, P1 completed. But P1, if you notice, this is very important. P1 only has 5 units of compute that it requires. So the first time, look at this. Again, this is the important part. P1 spent 1.5 units here, 1.5 units here, 1.5 units here. So total 4.5 units are done. Now when it runs here, only half a unit it will take up because it's only left with half a unit of time that it needs on the CPU. So at 10 units of time now, look at this, at 10 units of time, P3 gets scheduled, right? Now there is nothing else to compete with P3. P3 will complete 1.5 units of time and it again goes into the queue. In the queue, there is nothing. So P3 again gets scheduled. Now so once you have this whole big picture, once you have the Gantt chart and the ready queue with arrival times, again, this is the front of the queue. This is the rear of the queue. Okay. So once you have this, then it's very easy to answer the question. What is the question asking us? The question is asking us the second last time when P3 enters the ready queue. The second last time. Okay. So where is our ready queue? Look at the ready queue. This is the last time that P3 is entering the ready queue. This is the second last time when P3 is entering the ready queue. The second last time that P3 is entering the ready queue is 9 units of time. So the answer is 9. Right? The question here is that, okay, very commonly people write the answer as 10 because they misread the question and say, they misread the question. They don't see the timestamp at which P3 got added to the queue. The second from the last time. They misread it as the second time that P3 got scheduled. The second last time, I'm sorry, the second last from the end, the second last time that P3 got scheduled, and they answer it as 10. Okay, it's a very common silly mistake. So for this question, all you need to know is just how round robin works. the ability to draw the Gantt chart carefully, and the ability to draw the ready queue with the arrival timestamps. If you understood the whole algorithm of how round robin works, this is straightforward except for just this tricky statement. Okay, we have solved tons of questions, right, about how round robin itself works. I think I've solved tons of PYQs in the course videos also, right? So again, because it's slightly lengthy, I've just pre-drawn all the diagrams for ease of explaining, and because it requires also more space. Okay, cool. So let's get into the next question. Again, we are giving a mix of easy and hard questions. Sometimes we want to give easy questions. Again, the easy and hard are just about GATE standards. And if you notice, last 5 years of GATE, they're really not giving hard questions. They're giving slightly tricky questions. There are very, very few hard questions. I think less than 5% of GATE questions in the last 5 years are hard. Most of them are medium with a little bit of trickiness in them. Again, if you're getting demotivated because you're not able to solve these, it's perfectly okay. Please go back to the drawing board, learn from the course videos, go through the solved problems where we solve these step by step, go through the practice questions that we have, right? It's perfectly common not to be able to solve some of these questions. That happens to everyone. Okay, it's perfectly all right. All that it tells you is that you need more practice, and especially with practicing problem solving, not watching just theory. It tells you that you have to see how other problems and PYQs and solved problems have been solved by us in the course videos. Or if you're not a course registered student, just see how others have solved these questions. It all points down to you either not understanding the concept or not able to apply the concept to simple problem solving exercise problems. Both of them are covered in lots of detail in our course videos. So if you're a course registered student, please revise that. You will feel much, much better in the next iteration. Again, if somebody needs help with preparation, please do reach out to us. We'll try our best to help as many as we can. I think the question says round off to 2 decimal places, right? So please try to round it off to 2 decimal places, because in GATE, a computer will check your answers. So you have to be careful with that. Again, I see answers all around the place. So please be careful with your answers. This is straightforward. If you know exponential averaging, this is straightforward. That's why it's an easy question. Okay, a bunch of you have answered the question. Good. But just round it off to 2 decimal places and not 3. I'm happy that a good chunk of you at least know the concept of exponential averaging, know the formula, how it works, all of that. It's actually fairly easy. Again, exponential averaging is a concept that's used across science, not just in operating systems. I've encountered this in biology, in machine learning, in computer networks. It's a general concept in whole of science and mathematics. Cool. A good chunk of you have got the answer right. So let me go ahead and explain the solution, right? So again, the whole concept of exponential averaging with a smoothing factor of alpha, the formula that you should know is the predicted value of the next burst at time n+1. The predicted value is alpha times the observed value. I'm writing observed values with lowercase. Again, different people write different notations. Our alpha is 0.5. This lowercase tn is the observed burst time at timestamp n, plus 1 minus alpha tn. This is the predicted burst time in the nth interval, in the nth run. Okay, so the word used here is run, right? So what is given to us? We are given that alpha is 0.5. The initial guess is 6, which means T1 is 6 because the initial predicted value is 6. So using this, okay, this is your T1 because these are the actual values. This is your T2, this is your T3, this is your T4. What we are being asked here is the next predicted time would be dash units. So let's go and compute that, right? So what is a T2? T2 is, this is half, which means this will also be half. So I can write it as half of Tn. Tn, what we observed is 2. So 2 plus what we predicted earlier was 6. So this becomes 4. Now what is T3? T3 is half of what we observed, which is 7, plus what we predicted, which is 4. Right? So this becomes 11 by 2, which is 5.5. Now let's look at T4. T4 is half of what we observed, which is 11, plus what we predicted, 5.5. Right? So this is 16.5, which means this will become 8.25. Now what is T5? What we want is T5, right? Because the next predicted burst time would be, this is the answer that we are looking for. It is half of what is predicted, 8 is predicted. And what is the actual value? 8.25. Notice that this whole exponential averaging, slowly our predicted value and the observed values are getting closer and closer. Very, very interesting observation there. Okay, so this will be equal to 8.125 because the middle number between 8 and 8.25 is 8.125. If you have to round it to 2 decimal places, it becomes 8.13. That's it. That's all is the answer. Very simple. So if you know the formulation behind the exponential averaging with of course a smoothing factor, this is simple arithmetic. Cool. So let's get into the next question now. Okay, I know that this is little hard. The code is little hard for people to see, but I couldn't fit all of this in a single page. So I hope you will zoom in or check it out. I can see it on my phone. I'm also seeing this on my phone. So I can see the code on my phone. Yeah, I can see it. Cool. So I hope you can, I'm seeing it on my phone. So I hope you can also see it. Again, I couldn't fit this whole code snippet in a larger place. The problem is if I zoom in this whole thing will go for a toss. That's the problem. This whole thing will go for a toss. That's the problem I have. I cannot fit in everything in one screen. Yeah, if you watch it on full screen on YouTube on a smartphone, I'm just using a smartphone, a mid-tier smartphone, it's clearly visible. Yeah, I'm sure it's, yeah, I think I'm also at 480p. Yeah, I can see this at 480p, yes. Yeah, I try to squeeze in everything into one page. Okay, I see people putting in the answer. Good, good, good. Just think through it. You just have to know how fork works because I also mentioned what getPID does. Even if you don't know Linux programming here. Again, somebody says that the exponential averaging concept, they did not cover it in an institute that he is learning. Feel free to use our notes. We try to cover most of the concepts that have been encountered in Gate. So you can use our notes just to see if something is missing. And if we missed something, do let us know. We'll happily add those concepts. Okay, I see people putting in answers. Again, think through little carefully. This is not hard. This is actually easy problem. If you know what fork does, what getPID does, this is actually easy. Again, you can just go to our website and in the resources, you'll see all the notes. So there is notes for every subject there. That is handwritten by our mentors. So again, it's all based on our course videos and some additional material here and there, primarily textbooks. Just go to our website, you will find it in the resources part. Okay, cool. Again, it's already 7:40, so I'll go a little fast here since some of you have answered. Let's get into the whole thing. The most important thing is, how does fork behave? Understand that fork returns 0, right? Fork always returns 0 to the child process, and fork returns a positive number, which is the PID of the child. It returns the PID of the child to the parent. Right? That's what it returns. Again, there is a third case which we need not worry in our case. It returns -1 if fork fails. If fork could not create a child process, it returns -1, which we did not, because nothing is mentioned about failure to create a child process, right? So fork returns 0 to a child process, and it returns a positive number, which is nothing but the PID of the child created to the parent. If you know this logic, this whole problem is straightforward. That's all is the logic that you have to know for this. Look at this. So let's assume that, so first the parent is running, right? So let's take parent, right? The parent, okay, calls fork. Look at this, the parent calls fork. So let's see what's happening in the parent and in the child, right? So in the parent, what's happening? When parent calls the fork, the PID in the child becomes 0. The PID in the parent, look at this, the PID in the parent becomes the child ID, and it says the child PID is 10. So the child's PID is 10, the parent's PID is 2. So PID equals to 2 for the parent, PID equals to 10 for the child. So what will the parent get? The parent will get 10, the child's PID, right? Now both child and parent will keep running, right? They keep, because this is basically forking new processes, both of them will run. Let's see what happens in the parent's case. Okay, simple. So in the parent's case, if PID is less than 0, that let's assume that no error has occurred, else if PID equals to 0. PID will not be equal to 0 in the parent's case. Only in the child's case, PID will be 0. So this whole snippet will not even execute in the parent's case. In the parent's case, only this will execute. So in the parent's case, what will execute? PID1 equals to get PID. So PID1 is get PID, which means it will get the current process's PID. So PID1 here is equals to 2. Now, what are we printing? We are printing PID here, which is C, which means it will print 10, and D here, which will print 2. So C equals to 10, D equals to 2. Now let's look at the child process. In the child's process, let's assume there is no error that happened because nothing is mentioned about it. This will be executed and this will not be executed, because in the child process, PID will be equal to 0. And now what will PID1 be? PID1 is get PID in the child process. So the child process ID is 10. Now what are we printing? We are printing this as A, we are printing this as B. So the answer here is A equals to 0, B equals to 10, C equals to 10, D equals to 2. So option 4. Right? That's it. That's it. It's that simple. That's why it's an easy program. The reason this question is easy, because if you know what fork returns, if you know how fork works, the basic, you don't have to know the internals of fork. The basic functioning of fork, this problem is just about going through the code. Cool? So let's go to the next question now. Again, those of you who are facing problems with solving these questions, there are two fundamental solutions. One is, please go back. If you have a conceptual gap, please fill that gap. If you are not able to solve the problems because you have not practiced it enough, you have to go and practice. There are only two simple solutions. But if you need any other help, do reach out to us. We'll try and assist as many students as possible, with, of course, the first preference to the course enrolled students. Okay, while some of you are at it, Paras is asking, do we need to follow textbooks? Again, please, I think I mentioned this in the previous session also. Please watch the videos, or if you're joined an institution, any other institution, not ours, please follow their classes, finish the notes, revise the notes, solve a lot of problems. Textbooks only come if you have ample time still left. Your first priority should be to finish the videos, practice questions, test series questions, PYQs, all of that. If you still have time left, then please go and use the textbooks. You don't need the textbooks for gate preparation, because we try to take the best from all these brilliant textbooks and try to put it in video format so that it's crisper and it's easier and you can prepare it in shorter period of time. Cool. I'm happy that many of you are getting the answer correct here. Good, good, good. Good, good, good. Okay, I think most of you got it right. So let's get into the solution. This is an easy problem. Again, we are putting in a few easy, a few medium problems. Okay, we all know how this works. Okay, so look at this. What does it say? S equals to 0. So at the very beginning, S equals to 0 and T equals to 1. Right? Now let's assume P1 starts. Okay, now P1, because you have this PS, it will get stuck. So P1 is stuck. Okay, P1 is just stuck. It can't proceed any further. Now P2 will start. Because T equals to 1. Look at this. Because T equals to 1, P1 is stuck. Let's write down. Let's assume this is the time as time progresses. Now P2, what happens? With P2, it does PT. With PT, what happens? T becomes 0. It will print 0, 0, 1. And then it does VS. Now what happens? Now S becomes 1. Look at this. Now S becomes 1, and the whole, because it's an infinite loop, it will keep going through this. Now the moment S becomes 1, P1 can get unstuck. Right? Now P1 can get unstuck. Because PS now will make S equals to 0. It will print 0, 1 followed by 0. Remember, when this is happening, remember that T equals to 0. Right? Remember, see, this PT, again, when it goes up, it can't jump into this loop because T is currently 0. It can only go into the loop after this VT is executed. That's the important catch here. It's a very simple catch. Right? So, okay. So now P1 gets executed. This is S equals to 0. P2 can't execute at this point of time. So you will print 0, 1, 0. After it prints 0, 1, 0, then you have VT. Right? Now what happens? T becomes 1. Because T becomes 1, P2 can start. When P2 is executing, P1 can't execute because S equals to 0. So what do you get? You get 0, 0, 1 printed first, followed by 0, 1, 0. And this keeps getting printed 0, 0, 1, 0, 1, 0, so on and so forth. So what's happening here is 0, 0, 1, 0, 1, 0 is getting printed 1 or more times, not 0 times. 1 or more times till the time you kill these processes. Till the time you kill these processes, this will keep repeating. Right? So C is the right answer here. You can't get 0. That's why you can't get this result 0 times. Hence, this is not the answer. This is the right answer here. Right? Cool. Again, you can never get 0 times. That's why this is not the right answer. Because once the processes start, they'll start printing these values, right? Cool. Let's go to the next question now. Okay, this is also a good question. This is also an easy question if you know about the basic concepts of mutual exclusion, progress, bounded weighting, and things like that. Again, we try to give a mix of easy and medium problems because typically easy problems, you could encounter them for 1 mark, medium sometimes 1 mark, but mostly 2 marks. Okay, I see people putting in answers. Just think through it. Again, this is standard textbook example actually. I think this whole example is also taken from a standard textbook if I'm not wrong. Is it William Stallings? I'm not sure, but I think this same terminology, I remember seeing it in William Stallings. I'm not sure, but I think. Okay, a good chunk of you got it right. The answer is there is no progress. Again, if you notice this code, this is a very standard code snippet that you will encounter, and that is called a strict alternation, right? Which means what happens now is first P0 will run, then P1 will run, then P0 will run, then P1 will run. It's called the strict alternation case. Very standard case that you will encounter in most textbooks, which I've also covered, right? I think it's this example I think is there in William Stallings if I'm not wrong. That's why we called it easy, because I think I've also explained this with very similar example in the course videos. Okay, it uses the turn variable, right? So with strict alternation, you know that it guarantees mutual exclusion, right? Because if turn equals to 0, look at this, if turn equals to 0, right, then P0 can never run, right? P0 can't run. P0, look at this, if turn equals to 0, P0 is stuck in this for loop. Only P1 can go into critical section, right? So sorry, the other way around, I'm sorry. If turn equals to 0, my bad. If turn equals to 0, what happens? This case is false, so P0 will be executed. I'm sorry, if turn equals to 0, P0 will be executed, P1 will be stuck, right? P1 is stuck, my bad. Okay, I misread this as equal to. If turn equals to 1, then P1 will get executed and P0 will get stuck. Again, 0 means P0, 1 means P1. Yes, that makes sense, right? So this guarantees mutual exclusion. So mutual exclusion is satisfied. The question says what is not satisfied, right? Again, bounded waiting is also satisfied because we only have two processes now, and one of these two processes will get the process in strict alternation. The tricky part sometimes is with the progress. That's where many people sometimes get confused. Again, it's a standard example. Notice what happens in this case. Okay, you have P0. Let's assume P0 ran through the critical section. It made turn equals to 1 and it is running the other code. Let's assume P0 is running the other code. Let's just say when P0 is running the other code, let's assume it got preempted. P1 starts executing, right? Now what is turn? Turn equals to 1 now. Because P0 made turn equals to 1, so our turn variable now is 1. Right? The turn variable became 1. It is now executing the other code, and turn equals to 1. It got preempted, so P1 starts executing. So P1, let's assume, goes into the critical section, completes the critical section. Once it comes out of the critical section, what does it do? It makes turn equals to 0, right? And it goes into its other part of the code. Cool, all that is going good. Now, if P1 wants to again get into the critical section of the code, imagine if P1 wants to get into the other section of the code. Notice that P0 is still in the other part of the code. Let's assume P0 for some reason it's still in the other part of the code, right? P1 now can't get into the critical section because turn equals to 1. Only when because turn equals to 0. P1 can get into its critical section only when turn equals to 1. Now look at what's happening here. P1 is not able to progress. Even though P0 is not in its critical section, P0 is outside the critical section, it's in the other part of the code, right? It is there in the other part of the code. So what's happening here is, while P0 is in the other part of the code, P1 is not able to enter its critical section, right? Which means P1 is not able to progress, right? So which of the following is not satisfied? Progress is not satisfied. Again, this is a very, very nice example that you can see in the William Stallings book, if I'm not wrong. I remember reading this whole thing in a textbook about strict alternation. Sorry, it's a very standard example, right? Cool. So let's get into the next question. I think 8th question is one of the this is a very interesting question. I think this was the best question when I was solving these questions. Okay, so let's answer the 8th question. So we have 3 more questions. Most likely we'll finish it by 8 p.m. In case we get little stretched out, I might take 10 more minutes of your time. This was a good question. I think this was taken from some assignment at IIT Madras, if I'm not wrong, or a final exam question at IIT Madras undergrad computer science. I think this is one of those questions, if I'm not wrong. Again, when I was solving, this was one of the interesting questions that I found to be interesting. Again, some of these questions are also modified versions of some previous year questions, but we try to create questions as original as possible. But I cannot guarantee that all these questions are original. I mean, we don't guarantee that. Only in our mock tests, we give completely original questions made by our team. Good. People are making progress. They're able to solve consecutively problems and gaining confidence. That's good. Again, let's be very clear. All these problems need not be original problems. Some of them have been created by our team. Some of them have been modified based on exercise problems in textbooks. Some of them from assignment problems. Some of them of slightly modified versions of PYQs. Again, this is all for practice. This is a slight modification of or a variation of dining philosophers problem. I really like this problem because it's not hard, it's simple if you think about it. Okay, as I expected, answers are all around the place. People are saying A, B, C. Okay, nobody's saying D yet. Okay, cool. Again, read the question very carefully. Which of the above statements must be true to deny a request, not to grant a request, to deny a request for the first chopstick by a philosopher? For the first chopstick, that's very important. Okay, you have to be careful when you read the question. It can be slightly confusing, so please read this statement carefully. Read what is being asked of us. Which of the above statements must be true to deny a request for the first chopstick by a philosopher? Read the question. This statement, this is where I think many people will mess it up and get confused. So please read this statement very, very carefully. I think most of the reasoning behind getting the wrong answer is that statement. Okay, I see a lot of answers. Wow, you guys have solved this question much faster than I did when I was trying to solve it, because anyway, that's good. This question took me a little while to solve and I had to be careful not to mess it up. It was fun solving it. Cool. Okay, so let me get into the solution itself, just in the interest of time. So let's go here. Okay, so all this stuff, there are these 2 rules. Cool. The question says, which of the above statements must be true to deny a request for the first chopstick? That's important. So let's take only S1 case. If you have only S1 case, what does that mean? That means S1 equals to true and S2 equals to false. Right? So if S1 equals to true and S2 equals to false, let's see what does this mean? There is no philosopher with 2 chopsticks. Okay, so let's assume we have philosophers P1, P2, so on up to Pn. Of course, you have to draw a circle. I'm just drawing a line here. Just imagine this to be a circle. So there is no other philosopher with 2 chopsticks, which means all philosophers can have 0 chopsticks or 1 chopstick, right? So 0 or 1 chopstick. And second case is false. There is only one chopstick remaining, which means there are multiple chopsticks here, more than one, at least two, could be more than two. Now, if one of the philosophers, let's say this philosopher is requesting for a chopstick, why should you deny that request? You can comfortably give that trick. You can comfortably assign this chopstick to this philosopher. Why are you denying it? You don't have to deny it, right? So this certainly is not the right option. Okay, now let's look at the second case. What does the second case say? The second case says only S2, which means S1 equals to false and S2 equals to true. So what does this mean now? This means, look at this, you have philosopher 1, philosopher 2, so on and so forth, philosopher n. S1 equals to false, which means there is at least one philosopher who has two chopsticks. So let's assume this philosopher has two chopsticks. Some philosophers have 0 chopsticks, some philosophers have 1 chopsticks. There is at least one philosopher who has 2 chopsticks. And the second case, there is only one chopstick remaining. So there is only exactly one chopstick remaining. Now look at this. Now why would you deny the request? Because you can give this, suppose some PI is requesting for it, give him the chopstick, because there is at least one philosopher who has 2 chopsticks. He will consume his noodles or rice and he will give up both of them, and hence avoiding a deadlock, right? So that's not a problem at all. So even this is not the answer, right? Now let's see if C is the right answer. We don't know. So let's see. So the C says both S1 has to be true and S2 has to be true. Now what happens in that case? So we have philosopher 1, philosopher 2, let's say philosopher n. So there is no philosopher with 2 chopsticks, okay, which means all philosophers have 0 or 1 chopsticks. Now there is only one chopstick remaining. If there is only one chopstick remaining, what does that mean? It means, look at this. This is the most interesting part. What does this mean? This means there is one philosopher who has 0 chopsticks. Rest everybody has 1 chopsticks, right? Because none of them have 2 chopsticks, and there is only 1 chopstick left here. Now look at this. Now look at this. If this guy is requesting for a chopstick, then you should deny it. Because if you allocate this chopstick to this guy, every philosopher has one of them and they're in a deadlock situation. That's what happens, right? In a dining philosophers. Every philosopher has 1 chopstick and they're stuck in a deadlock, right? So this is the deadly case. This is where you deny the request for the first chopstick. Remember, if any other guy requests it, it is a request for the second chopstick. There is only one guy who can request for the first chopstick. It is this guy. And the moment you allocate it to him, this guy will have 1 chopstick. Now every philosopher has 1 chopstick, which means you got into a deadlock. So this is the deadly case, and hence C is the right answer here, right? It's very interesting problem. Again, the magic is all here. This is where a lot of people will, as I told you, this is where a lot of people will mess it up. Okay, which of the statements must be true to deny the request for the first chopstick by a philosopher to avoid deadlocks? Again, this statement is the crux of everything, right? So please be careful with that. Cool. Again, this problem is not hard. If you know dining philosophers, this is a straightforward application. The problem is medium and not easy because of the framing of this statement. That's what can make it very tricky. Okay. It's okay. It's okay. This is one of those medium but yet tricky questions. Okay. Let's go to the 9th question now. This is simple and easy. Okay, glad to see people putting in answers. Good. This is easy problem. I think S1 could be slightly tricky, but if you get that, it's straightforward. Yeah, so S2 is surely true. That's something that we all learn about the importance of implementing weight and signal atomically. That's like no-brainers. Okay, cool. So since most of you have put in your answers, let's get into the solution itself, right? So consider the following statements. Interrupts are an effective way to implement synchronization primitives in a multi-processor system. No, they're not, because imagine if I have multiple processors, not processes, processors. Think of 8 core or 8 processor systems. You have processor 1, processor 2, not processor, right? You have processor 3 and processor 4. Let's say you implement synchronization on this, or sorry, effective way to implement interrupts. So suppose, imagine you have interrupts here, or interrupts are an effective way to implement synchronization primitives. Okay, you have you have implemented interrupts here. You have implemented interrupts here. There are no interrupts here, right? Because in a multiprocessor system, it doesn't say anywhere that every processor implements the synchronization interrupts. Sorry, it doesn't say every processor implements it. Every processor is also a resource. So because you have multiple processors, right, you can't guarantee, interrupts are not the effective way to implement synchronization, right? So because if it said a single processor system, that's a logical thing to say. But if you have a multi-processor system, that may not work, right? So this statement is obviously false. This is trivially true. And the reasoning behind is this. Imagine you have process 0 and process 1. Imagine if this calls wait while it is decrementing. This wait, imagine it could so happen that if wait is not an atomic statement, and you can, you imagine you have a situation where this has decremented and this has also decremented. Then the whole system goes for a toss, right? It's a very commonsensical, the whole idea of having atomic operations itself is to, the whole reason semaphores work is because wait and signal can be implemented atomically, right? So S2 is true. So what do you have? What is the answer here? S1 is false, S2 is true. So B is the right answer. Okay. So let's go to the last question. We have already overshot by 5 minutes. This will be the last question. Again, this is also a very simple question. Please read the question very carefully. I know some of you will make a mistake here, so please read the question carefully. Okay, this will be the last question. We'll pack it up in another 5 to 6 minutes. Okay, so please try to answer this question. This question has a small trick. Many of you will mess it up. So please read the question carefully. So somebody is asking about test series. Test series questions will mostly be medium and some slightly hard. You will see fewer easy questions. And in test series, we try to give much more solid questions. I told you, I know people will make a mistake. I see answers 19, 10. Okay, those are the two answers I see. I know people will not read this question. This is an easy question, but you should read it, guys and ladies. Okay, 10 is not the right answer. Now please rethink. I've seen so many people put 10 as the answer. 10 is not the right answer. I hope I am right. Anyway, we'll solve it together. 99% 10 is not the right answer. So please rethink. Please read the question carefully. Yes, as Vishal rightly said, this is not a counting semaphore. It's a binary semaphore. How did you miss that? Now, if you realize that it's a binary semaphore, the answer is staring at you. Yes, such questions are common in GATE because people who set the gate question know that this is a simple question, but they also know that 90% of people will make a mistake here. They know it because they've seen generations of students. It's a binary semaphore. Okay, let me explain the answer in the interest of everyone's time. So what happens? S is initially 0. Remember that it's a binary semaphore, which means it can take only 0 or 1. Assume that no blocked processes are there at the start. Then you have 4 P's. Okay, so with the moment you have 4 P's, what happens? You have 4 blocked processes. Right? You have 4 blocked processes. Right? Then you have 6 V's. What do the 6 V's do? Each V will unblock it. So the 4 becomes unblocked. The 4 processes will now become unblocked. The 5th process, what does the 5th process do? The 5th process will make S equals to 1. The 6th process will also make S equals to 1 because it can't increment it any further. Right? That's the key here because it's a binary semaphore. Okay. So this is done, this is done. Then you get 9 P's. Now the logic is simple. When you get 9 P's, what happens? 8 of them get blocked. 1 of them passes through, right? Because S equals to 1, when you get 9 P's, the first process goes through, S becomes 0, S stays 0 and 8 of them get blocked. Then you get 13 V's. So what happens with 13 V's? 8 of these V's will unblock it. So the 8 get unblocked, right? So the 8 of them will get unblocked. Rest everything will keep incrementing S, but S can only be maximum 1 because it's a binary semaphore. Then finally you get 16P. When you have 16P, the very first P will make S equals to 0, right? So one process will go through, 15 processes now will get blocked. So at the end, the number of processes at the end that are blocked is 15. That's it, right? It's a very, very simple question. If you're careful with it, if you read the binary semaphore carefully, this is straightforward. Okay, folks, I don't want to take any more of your time. Any questions that we could not answer here, please go to our website, which is gate.appliedcourse.com. You will find our notes there. You'll also just try to email us if there is anything that you did not understand, that you think is incorrect, that we should correct, or any suggestions in general, right? We'll try and answer as many as possible. Obviously, we give preference to course enrolled students first. Okay, tomorrow we have the next session, so see you again at 7 p.m. tomorrow. We'll continue on operating systems again tomorrow also. Thank you very much. Bye-bye.